Okay, so welcome to this week's Origins Colloquium. It's a real pleasure to have Reinhard Genzel giving the talk this week. So Reinhard received his PhD in radio astronomy, working at Max Planck Institute for Radio Astronomy in Bonn and University of Bonn. In 1978, he joined the faculty. Well, he was at Harvard CFA and then a Berkeley Miller Fellow, and then faculty at Berkeley in the physics department uh, to a full professor position before joining Max Planck Institute for Extraterrestrial Physics in Garching, Munich in '86 as a director. And he's led a wide variety of projects, which we'll hear about in relation to black holes, but of course also galaxy evolution. He's been honored by a number of awards, the Shaw Prize, Crawford Prize, and of course Nobel Prize in 2020 for the work of establishing Sagittarius A star as a black hole. So welcome, Reinhard.
Yeah, well, thank you for having me. Um, we just get started here first. My sharing has stopped all of a sudden. Yeah, yeah, yeah. Not good. Share again. Yes. All right. So, uh,
It's coming up now, I think, again. Yeah, hopefully.
oh God. Uh, my God, I'm sort of in a.
You need to restart it, or is it?
I don't know. No, let me go out, okay, and get back in. Jesus, I mean, I haven't had that for a long time. Such problems. Share and
Yeah, it was working just a second ago, so hopefully it wants to do it.
yes. Sorry, Jonathan, I've done that so many times, and
Let's see if it comes up again. Are you getting a different message now?
I've raised different messages, and
Okay, where something is so we see your desktop, I think, or your web browser.
bing. Oh,
But we don't see the presentation yet.
yeah, no, I understand that. I don't either, actually. Um, okay, let me see.
Maybe it's if you can share the desktop and have that on the screen. It's often the more stable way.
There we go. Okay.
Yeah, there we
Um,
go. Great.
uh, I hope we can now go. So the talk is about the issue of the growth and evolution of galaxies and black holes. Now, of course, the story with the black holes, as you may know, is first and principally a prediction by General Relativity about 110 years ago that if basically the gravity gets so strong that the escape speed, if you like, of getting out of the vicinity of a mass m is so large that it's greater than the speed of light, well then nothing will escape. There is going to be a predicted a event horizon, and the region within the event horizon and the region outside of the event horizon are basically decoupled. So this is a prediction 110 years ago, and the question now, of course, is that really true? I mean, is it really true? And many people have, of course, wanted to see actual evidence, and This talk will try to summarize where we stand in this. And it's amazing that this evidence took basically the last 50 years in different forms to mature. Now, the first real, possibility that these black holes exist came in the 1960s. First, when X-ray binaries were discovered, and then the more spectacular form were very, very strong and variable radio sources which were discovered. And when you look at these radio sources, like in this picture here, in the optical, you see what looks like a faint little star, very faint star. And then there's a little crud on the side. You see that? Well, that's actually what we call a jet, material which moves almost at the speed of light. Now, the interpretation of what we're seeing here took about 10 years of theoretical work. And the possibility came about that what we are seeing here is a massive black hole, masses of several hundred, several million to several billion solar masses, which are creating material at a very large rate. And then before the material disappears in the event horizon, and then of course in the black hole, you create a lot of energy, very efficiently so actually, and that was the proposal to understand what we now call quasars. And you will hear more about these quasars. But the quasars are very, very far away because the probability to have a lot of accretion is very low. So the question is, how do you prove that such black holes, if they really do exist, how can we prove them experimentally with astronomy? And the answer is, well, we initially we cannot use quasars, but if there are black holes nearby, and here you see two of the theorists, Donald Lindenbell and Martin Rees on the right side, who basically proposed, well, maybe these black holes are at the centers of galaxies, maybe some, maybe even all galaxies. And then they become bright if they have a lot of accretion, but maybe the more typical case are nearby galaxies where there's not a lot of accretion. So if you look in these nearby galaxies, maybe you can see whether there is a mass concentration in the center. So this is sort of in the end of the 60s when if you like, the hunt started on the observational side. I will tell you in particular about the attempt in the nearest center of a galaxy, namely our own, to see whether there might be a central mass concentration and that this mass concentration is a black hole. Now, so this started in the 1970s in the group of Charles Townes in Berkeley, a Nobel laureate for the invention of the maser and the laser, and I joined, as you heard, him initially as a postdoc and then later as a faculty member. Then also Andrea Ghez and others at UCLA also started a similar kind of a hunt with the Keck telescope. So you will hear what we've learned. Now, another way of looking for these black holes is to look for gravitational waves. In particular, if you have a binary system where then the gravitational waves leads to the decay of a binary orbit, and in the end, what initially was a binary of two, say, stellar black holes turns into a bigger black hole at the very end of this. And indeed, after about 40, 50 years, very much like in the Galactic Center, evidence could be first found for these kinds of objects about 10 years ago. Now, another way of going at all of this is to use very, very high resolution intercontinental very long baseline interferometry. That's actually where I did my PhD thesis. And there you can have telescopes, radio telescopes across the entire globe. and achieve enormous angular resolution and hope to see the innermost regions of such an active region. So these are the various techniques which have now been used, and it's remarkable that after 50 years of work on the experimental side, we now have indeed very strong evidence that general relativity is right and that these black holes indeed do exist. Now, let me say a few words about the experimental work which is needed. If you have a distant object like a black hole, then of course you would like to have very sharp images, whether that's in the radio, or whether that's in the infrared or optical, but even with gravitational waves, and that requires basically large telescopes with large diameters, and then you can get images of distant objects. Now there's a problem that light of a distant, say, quasar, has to move through the Earth atmosphere, and in doing so, basically the refraction of the waves distort the images, and the light the stars become basically fairly large objects if the seeing is not very good. And so a technique had to be developed to overcome this distortion by the Earth atmosphere, and that's called adaptive optics. Now, an even better way of doing this was already proposed by famous Arthur Michelson in the late last century, and that is to not use just a single telescope, but several of them, and bring the light together in what we would call a interferometer. And in fact, in the 1920s, Michelson and Pease put up such a device in California on the 100-inch telescope. And you see there's this telescope, and then on top of it you see these mirrors, if you like, which are these reflectors, and so you can effectively, create a very long telescope in one direction, and then if the light interferes, then on the right side, what you get to see is the interference of the light and so-called fringes. And the larger the distance between the mirrors are, the better the resolution. So that's the trick, and that has been the way the radio astronomers moved forward. In the optical, it's much, much more difficult because but at such short wavelengths, like in the optical, of course, then the atmosphere comes in, the issue of the adaptive optics, but also the time scales over which the Earth's atmosphere has any stability is milliseconds. In a radio, we're talking about minutes. So actually, while the idea to do interferometry came from Michelson already very early on, it wasn't really used until recently. Uh, Now, as I said, the radio astronomers are in a better shape, and in fact, the so-called Event Horizon telescope with participants all across the world, from South America and North America and Europe, have been able to actually bring telescopes together in the 1 millimeter range with an enormous resolution, a resolution which is thousands of times better than that what we can do in a single telescope. Now, I mentioned already the gravitational observatories, and they actually work also the way an optical interferometer works, by combining basically the distortions of space and time in an L configuration of such a device. You can test whether or not there are gravitational wave structures on a small scale. And then finally, we were able to push this technique, which I showed you already for the radio devices, into the optical near infrared region in Chile. What you see there is the so-called Paranal site of the European Southern Observatory, which has currently four 8-meter telescopes. So they are being used, of course, as single telescopes most of the time. But already from the very beginning of building the telescopes, the idea was maybe one could bring the light of the four telescopes together, correct for the delay line problems, correct for adaptive optics, and then get the resolution of equivalently a 200-meter telescope. And this is the machine we are using now. It's a fairly complicated experiment, but over time it turned out to be extremely successful, as you hopefully will see in the talk. So that's the kind of experiments people have been pushing for in the last years. Now, to overcome the adaptive optics issue, what we're doing now, and we're doing this in parallel, as you see here, by shooting sodium wavelength lasers in the sky. Why do we do that? Because we can use then the reflected laser light from the upper atmosphere coming back to the telescope to analyze the distortions of the wavefront for each telescope and then basically flatten the wavefront and get diffraction limited images. That's a technique which was sort of talked about and in fact realized in the American military in the 1970s. But now it's in fact a feature of all the big new large telescope machines. This is now the situation in Chile and our gravity experiment where we are using basically these lasers. And on the right side, you see we are basically focusing the lasers on an object, then it's scattered back by the upper atmosphere, and then we're using that signal to basically flatten the wavefront. Now let's talk about the Galactic Center because that, of course, is one of the really great successful areas where we've been able to make progress. It's the nearest Galaxy Center, only 27,000 light years away compared to the, to millions and billions of light years for the distant quasars. And so once you have big telescopes and adaptive optics, you can make sharp images like this here in the near infrared. And what you see is a very dense region of dense stars. So that's the central star cluster in the galactic center on a scale of fraction of a light year. And in the center of that, the green dot there marks the location of a very bright radio source, which the radio astronomers discovered actually fairly early on. It's called Sagittarius A star. And in a way, you could say that was sort of the hope or the guess that this might be, in fact, the center of the galaxy, and there might be a black hole there. So that's the situation. Now, how would you now test that there might or might not be a black hole here in the center? Well, you're using basically the motions of gas and stars to test the strength of gravity. It started off, as I said, in Charlie Townsend's group, by using infrared spectroscopy to look at the Doppler effects of ionized gas emission in the central region around this Sagittarius star radio source. And from that, they could measure the motions to be very large, hundreds of kilometers per second gas motions. And that was the first indication in the N70s that there might be a mass of a few million solar masses. Now, is it a black hole? Well, that wasn't clear at the time. There were, could have been a black hole, but it could also have been a concentration of faint stars, for instance, very compact star clusters. So you have to go a step further and actually, really measure the motions in detail. And to do this, we are measuring stars themselves in the infrared, measure their positions, and then over time we see them move. you need a lot of patience for this because although the motions turn out to be in part thousands of kilometers per second in near Sagittarius star, these are large distances, and it took several tens of years to make progress. And we made this experiment with the Paranal telescopes, and Andrea Ghez, Eric Becklin, and Mark Morris used the Keck telescopes in order to then study how fast do the stars move at different distances from Sagittarius A star. And the idea was just like in the solar system, if there's a central mass dominating the mass, well, then the stars coming closer to the central point would move faster, uh, Kepler's laws, and basically over time you can then get the orbits of these stars, and here you see the orbit of one of these stars, which both groups were able to construct from about 20 years of measurement. The Sagittarius star radio source is down there in the left side here, this dot. And this here is a few hundred astronomical units. And the star basically is on a highly elliptical orbit. And so initially, when we started the measurements with astrometry of the stars were up here, the star was up here, and it moved, at around 1,000 kilometers per second. But then, as it moves down this ellipse, it got faster and faster. And in 2002, both groups saw that star, which we call S2 or S02, had a velocity of about 8,000 kilometers per second. So clearly, there was a central mass. Now, is it a black hole? Well, that is not so clear because the distance of the star at the closest point here is about 120 astronomical units. So that's still, 1,400 times the event horizon size. There could be an object there, massive, few million solar masses, but does it have to be a black hole? That was sort of the next stage of the experiment, and that we, basically try to do with interferometry. Now, of course, if general relativity is true and there's a central mass, well, another way of seeing that effect of that mass onto the light of the stars as they orbit there is the gravitational redshift. Because basically, as light emerges from the central region, goes out, then of course the clocks go slower initially, and the light is redshifted in by about 200 kilometers per second. And we were able, and also the group in California was able to see this effect in early 2000s. So that was the first sort of a way to test also the general relativity on that kind of a scale. The next effect general relativity predicts are precessions. So in the classic case of a Newtonian mass with a planet around it, but only one planet, the orbit of the planet, if it's an ellipse or a circle, would stay always the same. Not so in general relativity. In general relativity, there are precessions. One, due to the space curvature, that's called the Schwarzschild precession. And the second one is if the black hole has a spin, then it's also this distortion of space-time near the black hole, which creates another precession. So there on the right side now we see the motion of that star S2, which you had seen before. But now we look at the residuals down below between the Newtonian orbit and then actually the measurements. And you see, as the star is far away from the orbit between 2000 and 2010, it was, there is not much of a difference. But then as you come close, and in fact near that Perry, in 2018, you can see all of a sudden that the residual motions of the star are clearly different from Newton. And exactly what general relativity predicts, this is the red curve. So this is the sort of the first fine detail evidence that indeed that the mass concentration is so large that in fact we can see the distortions of space-time which general relativity would predict. Now, in fact, we can do even more of that in our case by looking at the radio source itself in the infrared. And every few days, the Sagittarius star source, which is also an infrared source, brightens up by a factor up to several tens of factors of several tens. And when that happens, we, with our interferometric measurements, we can look at the positions of the light, and we see that the center of the positions moves in sort of an elliptical kind of a motion. The velocity of these motions are 30% the speed of light, and we are only now here at a few times the event horizon size. So that really does indicate that there must be a very concentrated mass like a black hole. Now, the radio astronomers also have done this, as I discussed this earlier, by combining at around 1 millimeter wavelength the light from telescopes around the globe, and the deviations of the light by gravity then allow you to see the central black hole or the central mass there in dark, but you see then there's a ring of bright emission, and if this is a object of a few million solar masses, the diameter of the ring should be about 50 microarc seconds. And indeed, that's exactly what they see. So that's the situation we are in right now. We have very, very strong evidence for a central mass of 4 million solar masses in the galactic center, and we can now ask the question: is that really truly a, a black hole with a spin? Now, for that, we need to come still closer. On the right side, you see again the blue curve is that orbit of the S2 star, but we would like to still go still closer. And that's technically challenging because now we have to look at very, very faint stars. And we have discovered one such star we call S301, which appears to have an orbital period not of 20 years like S2, but of only 8 years, and it comes very, very close. So then you can hope to see the effects of the spin. So in addition to the Schwarzschild precession, which for the star S2 makes a prograde precession of about 12 arc minutes, in the case of the star S301, the Schwarzschild precession is degrees in 8 years, and maybe we can see, in fact, also the spin. And so that's what we're doing right now to basically see there is that star in detail as we see it now, and indeed you see the Schwarzschild precession easy to see. It's 2 degrees per orbit, and the star is now at Apo and will come back inside and down to a distance of only about 100 Schwarzschild radii. And if general relativity is correct, we should be able to see the spin that way. That's called lens tearing precession. So this is really detailed physics at a distance of 27,000 light years. But we have every hope that this is an experiment we will be able to do in the next 10 years. Now, so what have we learned over the last 40 years? We've learned that the mass distribution in the galactic center, which you see here on the vertical scale versus distance from the center, is one where if you go far away into the cluster of the stars, is of course determined by an extended mass due to the stellar clusters. But as you come closer, and I showed you these different stages, As you go inside of about, a parsec or a few light years, then the mass does not change. It stays at 4 million solar masses, all the way to the central region we can now measure. And the accuracy of these measurements is really astounding. It's only about a tenth or two-tenths of a percent error bar, and we can go and see these flares. The radio astronomers can see this ring, and we can see the star S301, which I showed you, and the motions there. So the interpretation is that the central 4 million solar masses are within only a few times the event horizon size of a black hole. So that is relatively convincing, although, as physicists, we have to always be ready to still do better and really make sure. Now, let me get on one side of this problem. So there's a central mass, 4 million solar masses. The question is, how is there an extended mass around that black hole which we can detect? And the answer is yes, the stars. And what we find is that as you go further away from the central radio source, the stars are these red objects basically on near spherical orbits. So 1 minus e is relatively large. Now, if you come closer to these objects which have basically elliptical orbits, then you can see that the closer you come, the more elliptical the orbits become. The star S301 has an ellipticity of 0.998. That's incredible. How can that be? Well, around 30 years ago, a proposal had already been made then that this could happen by basically scattering of a binary into the central region. Then the three-body interaction between the central black hole and the binary can then disrupt the binary, and one member of the binary gets stuck, and then it's really sort of in a highly elliptical orbit in the very center, and that's what we think we see. Other than these stars, which we can detect with the interferometer and also the radio emission, there's very little mass else. So the central region, astonishingly, is relatively low content of mass. You see this in the lower right. We can set a limit of about 1,000 solar masses within the orbit of S2. 1,000 solar masses compared to the 4 million solar masses of the central source, and that tells you that basically stars, when they come into the central region, are probably fairly easily either attracted by the black hole or destroyed by collisions. So we are learning something about the star cluster as well about the central black hole. Now let's go to other galaxies and ask the questions. So do they truly also have such central masses? And so many people have, for the last 20 years, looked at the motions of stars and gas in and nearby and not so nearby galaxies, and basically plotted what they would measure as the central bulge or central core of the galaxy on the horizontal scale. So you see 10 to the 9, 10 to the 10, 10 to the 11, 10 to the 12 solar masses. And then on the vertical scale, the central mass. And you can see there's a correlation, a rough correlation. Uh, the more massive the central bulge of a galaxy is, the more likely it has a very massive center. And so the interpretation from the very beginning, when that was found, say in our nearby galaxy Andromeda there on the right side, then the interpretation is what you're seeing here is a correlation between the mass in the center of a black hole with its host galaxy. And if there's such a correlation, that tells you that they must have been correlated in their evolution, because the evolution of the galaxies takes billions of years. And in fact, when you divide the central mass, which you interpret as a black hole, versus the bulge mass, and you see is approximately constant. And from this, you can then basically say that it looks that as if about 2 to 5 by 10 to minus 3, so zero point 0.2 to 0.5% of the mass of the bulge is in form of a central object, which you might think is a black hole. That's very well studied now, and a remarkable thing, as you will see in the second, is that this happened. This correlation actually happened early on. Now, how would that happen? This by basically growing the galaxy from material coming into the galaxy, and some of that gas then actually goes under the central black hole. And the growth time you would expect by a factor of two is about 400 million years. So it takes a long time to develop these very central large masses. Now, what we can do nowadays is we can actually, using our gravity interferometric experiment, to look at distant quasars and galaxies and look at the region surrounding it. That's typically ionized gas called the broadline region. And so the picture is there might be a central massive black hole that is surrounded by this red region called accretion zone. And then surrounding that, there is ionized gas, which is basically moving forced by the gravity of the central objects. And so we can ask with our interferometer, is there a evidence that this broadline region correlates with the mass of the central object? And the answer is yes, absolutely. Here, for instance, is this first quasar, which I showed you in the very beginning, 3C273. And what we do is we take hydrogen recombination lines, in this case Paschen alpha, and we use the interferometer to measure the position in blue of the different parts of the line. And as you see, the left parts of the line are slightly displaced from the right part of the line by a small amount, only a fraction of a micro arc second. And that looks like a rotation. And so if you interpret the rotation as due to a mass, then you can measure the mass of the central black hole. And that's exactly what we can now do for distant objects. Not only for 3C73, which is still fairly close, but actually we are now looking at quasars in the early universe. And again, you see this S-shape phase shift around H alpha in this particular case. And we can begin to measure the masses precisely of these early active galaxies, the quasars. And what we find is that the central masses were formed very, very early on. How early we don't actually know right now. I mean, the James Webb Telescope discovers ever more very, very high redshift objects, and we're using the interferometry to see that the black holes actually were, relatively speaking, more massive than the host galaxies than at later times. So clearly, there are processes which we don't understand, maybe going all the way back to the Big Bang. And some people are speculating that you could have formed the first massive black holes right after or during the Big Bang itself. Incredibly exciting story, but one which, of course, will take us years to understand how such early black holes formed either by very fast accretion, by the collapse of an early star cluster, or by having black holes formed during the Big Bang itself. So this will take many, many years to understand. Meanwhile, of course, we have sort of a picture of how the growth of galaxies and the growth of black holes come together. The mass in galaxies, we strongly believe, is dominated by the so-called dark matter. And then as universe expands locally, these filaments of dark matter form the first galaxies. Material streams in, and then after a while, typically after a few billion years after the Big Bang, you form central black holes, and these black holes then start accreting, and then you throw out gas again from the center through the activity of these quasars. So that's the picture we have now. Broadly speaking, in excellent agreement with the data, but as I told you, the details, need to be still made more certain. But it's a very exciting story, which, on the one hand, we have the experimental evidence, and here, on the other hand, we have ever better theoretical simulation to understand. Now, what about the future? What do we expect we can do in the future? Well, right now, the star machine is the James Webb Telescope of NASA, telling us about the first objects, the first quasars. The next big machine is the ESO extremely large telescope, a 40-meter telescope we're building in Chile next to the Paranal site. And then, of course, we also would like to have a very high resolution machine for looking at gravitational waves in space. That's called LISA. So in 10 years from now, we might have a combination of very big telescopes on the ground, telescopes in space, as well as these machines detecting the gravitational waves. And then we can hope to basically get at the ultimate proof of general relativity's expression, the so-called no-hair theorem, namely the fact that a black hole, according to general relativity, only has three quantities: the mass, a spin, and basically the amount of uh, the material surrounding it. And so this no-hair theorem says that according to general relativity, the black holes are very simple objects. Very simple objects. The quadrupole moment, for instance, is totally determined by the spin of the black hole. Now, this will take, I'm sure, many, many years, and maybe some of you young people will have a chance to participate in this exciting continuation of the fund for these black holes. Well, tough luck.
So thank you, Reinhard. That was great. Thank you very much. So we have time for questions and the discussion. So if maybe Aish and Virginia can help me with their questions there. If you're on Zoom, just raise your electronic hand. And here, Winter's already raising her hand. So Winter, please.
Hello. Thank you, Gonzalo, for that great talk. I was just wondering about the last thing you said when you were talking about the three qualities of a black hole. Before, when
Yes.
I've heard people talk about that, like I've always heard that they have mass, spin, and charge. But you said like the quantity of mass orbiting it instead. I was
It,
just
it, yes, you're right, of course. That's true, actually. But for the astrophysical black holes we are discussing here, the charge is probably not all that relevant. Why? Because if you have a charged black hole in somewhere in the center of the Milky Way, for instance, then immediately there will be a current discharging the black hole. So while it is true, and you're absolutely right, that general relativity allows a black hole to have three properties, mass, spin, and charge, we think that for the black holes we are studying, the electrical charge is likely not very relevant.
oh,
Okay, so maybe we can focus on the work on the Galactic Center first and then come to the more distant black holes that you mentioned. You mentioned these infrared flares. Is that then understood why is there any periodicity in the flaring at all, or do we understand?
Yeah, there is in fact. Let me see where the flares.
And perhaps you could, what is the accretion rate to the black hole, and is there?
Yeah, in the galactic center is minutiae. Okay, 10 to minus 8 or so, 10 to minus 6 to 10 to minus 8 solar masses per year. So this is only a very, very small fraction of the Eddington rate, right? So
Yeah.
in contrast to the quasars.
Hmm.
Now, but what we believe is happening in these flares we can see is that the central region in our galaxy, because there is not all that much material around it, is dominated by magnetic fields. So it's a magnetically dominated situation. And in such a situation, you can have reconnection events. And these reconnection events then accelerate electrons to very high energy. And it might be these events which we see as flares in the infrared. And indeed, the emission we see from these flares is polarized, and we can see the polarization rotate along with the motion of the flare. So it's exactly what you would expect from a magnetized little hotspot, which then lasts for a little while. Then, of course, after a little while, meaning say one turn around the black hole, it gets tidally sheared, and then it basically disappears, and then it takes another few days until maybe you get to see another one.
And do we think it's a two temperature plasma and there's advection dominated accretion?
Yeah, it's a traction-dominated accretion, and what we can actually say at this point is that the ratio of the magnetic energy density near the event horizon, so B squared, where B is the magnetic field over 8 pi, is about yeah, 5 times larger, 6 times larger than the gas density. So that's unusual. That is not what you would expect in a quasar. In a quasar, you would actually expect that the gas pressure is the dominant energy carrier because there's so much accretion, but not in the galactic center. That's a magnetically dominated situation.
Mhm. I see there's a question, Virginia. You can go there next and we'll come back. Okay.
Yeah, thank you, Reinhard. I wanted to ask about the signature of the lens theory precession from star S301. With a single star, are you able to tease apart the relative orientation of the black hole spin and its magnitude, or do you need more stars than one to do that?
No, you can principally you can do it from one if you can really fully analyze the orbital orientation, which we cannot yet. We see the motion of the star, yeah, and so we would see the precession, but we don't have a spectrum yet. That star is so faint that with the current spectroscopy we have, we cannot see uh, in which direction the orbit is tilted. And so that is something which we need to do if you really have full information. But you're right, of course. We actually see now in this innermost region every year uh, two, three stars going through Perry. And so if these, very close to the black hole stars are common, then of course, over a longer period of time, you would expect to get statistics on the entire structure of the space-time.
Could I ask a follow-up question, which is that with such a close passage, there might be tidal distortion of the star, and that might also, I'm not sure I got the physics right, but that might also change the orbital signature.
Yeah, there's all kinds of things which can happen. I mean, uh, the star we are seeing, S301, is a remarkable almost 20th magnitude in K-band. I mean, when we started this whole game 40 years ago, we would have not dreamed to see such faint stars. Uh, so it's probably, we think, a 1.2 or 1.3 solar mass main sequence F star. But suppose it isn't. It could be a giant. If it's a giant, then in fact, its Perry approach is so close that it could be tidally partially disrupted. And so we will see in about 10 years what will be true. Okay. So you're quite right that there are additional physics effects, tidal disruption events, and so forth, which may very well become accessible to the measurements.
Thank you.
Mm-hmm. We get Sagnik next and then Sadia.
Great talk. I just had one question that if like is there a possibility to understand the accretion history and the how the orientation of the black hole axis changes with time? Like
Yeah, yeah, absolutely. And I couldn't get into all of these details. So the most naive way of looking at this in a quasar is that you would say, well, these quasars are very massive black holes in very massive galaxies. And we know from the simulations and also from observations that at a given time, there typically are preferential directions from the intergalactic medium where the gas is flowing into the galaxy. And so that by itself already tells you that there's a dominating angular momentum. Maybe you would say, well, actually, the James Webb measurements at redshift 5 to 10 now show that there are many spiral galaxies out there, so they have their disks. They're disk galaxies, and so then you would say there's a preferential direction in which gas would flow in, and would that preferential direction be seen at the central black hole? And the answer is maybe at an early stage with quasars, not in the galactic center. Why not? Because what's flowing in there, and we can measure the direction actually, is not determined by the galaxy or the plane of the galaxy, but it's determined by the angular momentum direction of the motions of nearby Wolf-Rayet stars. Okay, so we see that we can measure that direction, and we see that what ends up in the central region has still this angular momentum. And these Wolf-Rayet stars have different motions, and so if you like, on Mondays the accretion comes from the left side. On Fridays it comes from the right side, and so there is not a single buildup of angular momentum at the present time in our Milky Way.
Hmm. Is there any current constraint on the amount of spin of Sagittarius star at all?
Not yet. I mean, you have to wait. As I said, I think wait. I would say 10 years, and we should be able to make the measurement.
So what will we measure a direction and a magnitude of the spin?
Yeah, that's right. I
Hmm.
mean, obviously, I told you what the measurements we are already doing now would then lead to a return of the star to Perry that would be able to measure. Then the spectroscopy, which we can do on that star with the ELT, then probably give us the orientation of the orbit, also, in 3 dimensions. That is the information we need to get everything.
Okay, Sadia had a question.
Yeah, hi. Thank you so much for the talk. It was wonderful. I think in maybe one of the later slides you mentioned that the mass doubling rate was around 400 million years. Firstly, how do we know that? And
Well,
secondly, I mean, where
it,
does
it,
it? Oh, sorry. Yeah.
if you okay, so this is a classical theoretical limit derived from the so-called Eddington limit. So basically, the idea is the following: suppose you have material accreting onto such a black hole, and you increase the Eddington rate. I'm sorry, the accretion rate. Then at some point, the amount of energy which is released in the central accretion zone as photon pressure becomes so large that it starts affecting the incoming material, and there's a limit. That's
Mhm.
called the Eddington limit. So at the Eddington limit for a black hole like the Galactic Center, then the mass can double within 400 million years. So that's a long time scale.
Right.
Okay.
So it's just something else that confirms our theory, that probably confirms that the thing at the center is in fact a black hole.
Pardon? I didn't understand.
So is it just like another part of the proof that what we have in the center is indeed a black hole? Is that the role that it plays? Or
Yeah, well, okay. I mean, you can, I mean, I would say, if you allow me and you heard my talk, the progress which you've been able to make over the last 40 years is pretty remarkable.
yeah. Thank you.
I mean, initially when I was a student, yeah, of course, everyone knew about general relativity, but I mean, the interpretation of quasars as accreting black holes was a few people believed that, yeah, others didn't. So we are very far away from that situation now. I mean, initially, uh, when the gas motions were measured in the 1970s by Townsend's group, a few astronomers say, well, that looks pretty reasonable, but the physics community would not believe that to be convincing. But well, now we are at the limit where the 2020 Nobel Committee said a supermassive object, probably a black hole. Okay, so it still leaves open, of course, that you will still want to do more. And we are physicists. We have to exclude any other alternative, and there might be, who knows? There might be issues which general relativity does not write. And there's, in fact, one which I'm sure you know, and that's the small scale structure of the central singularity. The
Yeah.
general relativity predicts that in a black hole like the galactic center, all the energy mass is concentrated in a point, in an infinitely dense central point, and anything which goes inside the event horizon falls basically into that point. Is that true? Theoretically, there are many, many people who have fantastic ideas, string theory, and so forth, how that could be. Now, there we have a problem, right? Because in the case of the nuclear force or the weak force or all of those, and electromagnetic force, we would build bigger and bigger accelerators to basically get sharper and sharper images. This is not possible for black holes, right? Because the event horizon. Yeah, the event horizon is a natural barrier for information reaching us from the central region. Now, of course, you may have heard about the Hawking radiation. So there are, on small scales, also quantum phenomena, which would allow some amount of energy to come out. And if we can measure that, maybe we can say something about the central region. But I mean, at this point, it seems to be so far away from reality that I would say I would certainly not be willing to speculate.
Well, just to follow up on the Eddington issue, it was amazing that you could measure the masses then now to some of those Redshift 9 systems. So you can measure the Eddington ratio in these systems. What kind of
Yes,
accuracy?
in fact, I mean, Jonathan, exactly. That is our next big goal. I mean, um, we are, as I showed, we are able to measure the masses now directly from the motions of the ionized gas. And of course, what we would like to do is to get more detailed information. And that detailed information may very, very well either come from spectroscopy with the ELT. And the second thing is we are now already speculating about could we go from the few hundred meter baseline we currently have to a interferometer with another telescope or two and baselines of several kilometers. Then we would have the resolution to go sub micro arc second.
Mm-hmm. Well, we should finish up soon, but I would like to ask you about the emptiness of around Sagittarius star, and
Yeah.
if there were massive, well, even 10 solar mass black holes or intermediate mass black holes, you'd expect them to sink in near Sagittarius
That's
star.
absolute, yes.
So,
And in fact, I mean, that tells you, Jonathan, that what your theoretical initial insight might have been does not have to hold. So the initial insight, of course, was, well, if you have a spectrum of stars surrounding a big black hole, then the relaxation of those energies leads to a slow compactification and a cusp of stars near the black hole. Okay. And the oldest stars, and in particular stellar black holes, would form sort of a halo around the big black hole. Well, that may very well be, but the amount of material there that we measure now precisely is so low that basically, yes, there might be 10, 20 solar mass black holes in that region, but not so many. And that means, in fact, that there are other processes which had not been considered to, in fact, collide stars and then basically scatter them out of the entire region or let them immediately fall into the black hole. So the time scales which initially were considered, namely two-body relaxation, is not correct.
mm-hmm. Well, we should stop the main session now. So let's thank Reinhard again for a great talk and discussion.
Well, thank you for having me.